The purpose of this work is to present tools to encode data into DNA as a function of process constraints. So not a single encoding, but a recipe to produce such encodings. DNA data storage uses synthesis for writing and sequencing for reading as a constrained medium. As an abstract model, one can think of synthesis as adding base by base to a growing chain or strand. With respect to sequencing, there are at least two sequencing methods at present. One is nanopore sequencing, and the other one is sequencing using polymerase chain reaction, or PCR. On either synthesis or sequencing, PCR is used to increase the concentration of a DNA strand, and it is very similar to the function of an amplifier, which is also why we call it amplification. DNA synthesis is open to anyone, so starting from a file and a basic mapping from bits to bases, you can generate text sequences of bases and send them to a synthesis company through a web interface and get your data synthesized as DNA. If you are not aware of limitations on the data, this would be a point where the synthesis company would tell you about them, and they may reject some of your sequences, mark them as difficult, or price them differently. And these include homopolymers, GC content, GC variants, and short tandem repeats, which we'll explain immediately. Homopolymers are sequences that are made of multiple continuous repeats of the same single base. GC content is defined to be the ratio between counts of G and C in the strand and the length of the strand. Too much of it or too little of it might be a limitation. Variance of GC content between two adjacent stretches of strands, so one could have too much GC content and the other one has too little, or just the difference between them is too large. Short tandem repeats are sequences in which there are multiple consecutive repeats of the same short subsequence, and there could be a limitation on the number of consecutive repeats on such a strand. In addition, certain reserved short subsequences may mark where sequencing should begin, and their appearance in the data payload may result in fault. The way we treat these constraints in our work is by considering mapping bit sequences into DNA sequences of a fixed length, K, rather than single bases. The idea is to concatenate subsequences of length K that comply with all constraints, so that a constraint could only be violated at the concatenation point. The choice of K should be short enough that a symbol of length K does not contain any violation already. At the same time, note that there are 2K bits in a symbol, and if we're going to be reserving some of them to resolve constraints, then each reserved bit increases the overhead by 1 over 2K, so K should be as large as possible to reduce overhead. We enumerate the symbols, and we form a connectivity matrix so that A at coordinate ij equals 1 if symbol j could be concatenated to symbol I, and 0 otherwise. This allows us to approximate the theoretical capacity of this K symbol channel given in this equation. In the paper, we give an example of multiple constraints. The first one is maximal number of consecutive identical bases being 5, so 6 is a violation. If we focus on the row for symbol CCCC, we can see that no symbol between CCAA and CCTT can be concatenated to it. Finally, in this example, we have a limitation on GC content, which is allowed to be between 15% and 85% in the concatenated two symbols. So for example, if we want to focus on the orange square, we can see that CCCC cannot be concatenated to CCCC, for example. So when we put them all together, we get a matrix that corresponds to all constraints concurrently. And one, for example, could focus on the symbols being concatenated to TTTT, and one can see that AAAA could not be concatenated to it. For example, this could be because the result has too little GC content. But if you look at GGAA, it could be concatenated to it. So if we were to reserve the first two bases at most, we know that we could resolve that conflict or that restriction for TTTT. Reserving bits on the right-hand side symbol corresponds to reducing the connectivity matrix. Specifically, splitting the connectivity matrix in half about the center and taking the coordinate-wise maximum between the left and right sides. Each such iteration corresponds to one bit reservation, and we stop once we reach a matrix with ones in all coordinates, or when we have reduced the original matrix to a single column. The example in the paper requires not one but 3 iterations, but eventually when you reach a matrix which has no zeros in it, that is the all one matrix, you can concatenate any partial symbol on the horizontal axis to any symbol of length k on the vertical axis. So far we haven't chosen any specific values for our reserved bits. We just calculated how many bits will be needed to resolve any constraints at the concatenation point. And in that sense, it's an easy tool to compare between different processes. To make this into a specific encoding, we need to retrace our steps, meaning how we got to the all-one matrix, and choose specific values for the bits we reserved in order to make any concatenation between two symbols legal. So continuing our example, suppose we have a symbol coming from the left saying AAAA, and another symbol coming from the right saying 0AA with 3 reserved bits. We need to choose one of the options for the 3 reserved bits so that there is no violation at the concatenation point. We could choose, for example, 1 to complement the 0, and that will give us a G, and we can choose, for example, a C for the remaining base which is reserved. We end up in a very natural way with a finite state machine where our current state is determined by a length k symbol, and upon input of a partial symbol and a choice of specific reserved values, we transition to the next state and output a full length k symbol. Our current work includes choosing the specific values for the reserved bits wisely, and that is also coupled to the next question, which is, can we use the Viterbi decoder for this, since this is a finite state machine encoding? If we manage to use the Viterbi decoder, this could be an error correcting code, and we could compensate for insertions and deletions. Thank you for watching, and we look forward to your feedback.